Most people think they understand what a black hole is. They don't. Because what I'm about to describe has no name that fully covers it. It weighs 100 billion times the mass of our Sun. By the laws of physics, it cannot exist. And after hundreds of millions of years of silence, it just woke up. Stop. Before I tell you what Phoenix A is, I need to tell you what it is not. It is not a black hole. Not in any sense that word was originally meant to describe. Not in any sense that fits the diagrams you've seen, the simulations you've watched, the descriptions you've read. It is a region, a territory, an empire carved out of space-time so large that light, the fastest thing the universe permits, needs 3 weeks to cross it from one side to the other. It weighs approximately 100 billion times the mass of our Sun. Our entire Milky Way, 200 billion stars, all their dust clouds, all their dark matter, everything, has a central black hole of about 4 million solar masses. Phoenix A could be roughly 25,000 times more massive than that, and, right, accounting for the travel time of light, it is feeding, furiously, on a scale that has broken its own environment and triggered a star formation event with no clear precedent in the modern universe. Here is the question nobody asks at the start of this story. If Phoenix A is this massive, and if the physics of black hole growth sets a hard speed limit on how fast they can grow, then how, in a universe only 13.8 billion years old, does something like this exist? The answer involves broken mathematics, a thermostat that failed, and a window into the most violent period in cosmic history. I'm going to tell you all of it. But first, you need to understand the universe we thought we were living in, because you cannot appreciate how completely Phoenix A has shattered that picture without understanding exactly what the picture looked like before it arrived. For decades, the textbook version of Bloggles was clean. You had stellar mass black holes, the compressed corpses of stars, violent, comprehensible, small enough to fit inside a city. You had supermassive black holes, the giants at the centers of galaxies, ranging from hundreds of thousands to a few billion solar masses. Enormous, but explainable. The product of billions of years of gradual feeding as galaxies collided and merged. Between those two categories, a gap we were filling in. Beyond them, nothing. That was the universe we were comfortable with. Then, in the early 2000s, observations started turning up black holes that didn't fit. Too big. Not by a little, by orders of magnitude. NGC 1277, an unremarkable galaxy, harbored a black hole originally estimated at up to 17 billion solar masses. TON 618, a quasar more than 10 billion light-years away, came in at around 66 billion solar masses. Astronomers reached for a new word, ultramassive, above 10 billion suns, maybe higher, maybe much higher. And then Phoenix. In 2010, the South Pole Telescope, designed to map the faint afterglow of the Big Bang itself, spotted something unusual in the southern sky. A faint distortion in ancient radiation, the signature of enormous amounts of hot gas collecting in one place. What the follow-up revealed was a galaxy cluster with a total mass of around 2 quadrillion suns. One of the most massive structures ever identified. They named it the Phoenix Cluster. It turned out to be the brightest X-ray source of its kind ever recorded. And at its core, sitting inside an enormous central galaxy, was a black hole estimated at approximately 100 billion solar masses. TON 618, the previous record holder, weighs around 66 billion solar masses. Phoenix A is roughly 50% more massive than the largest black hole anyone had found before. And that was the least surprising thing about it. To understand why Phoenix A breaks the rules, you first need to understand what it looks like in physical space. Mass and event horizon size scale linearly. Double the mass, double the radius. Our Sun, compressed to a black hole, would have an event horizon less than 4 miles across. The black hole at the center of our galaxy, Sagittarius, has an event horizon about 15 million miles across. Impressive, but our solar system swallows it comfortably. Mercury's orbit alone is 5 times wider. Phoenix A is something else. If the higher mass estimates are correct, its event horizon stretches approximately 180 billion miles from center to edge, end to end, a diameter of roughly 370 billion miles, approximately 100 times the distance from the Sun to Pluto. Light would need 3 weeks to cross it. A Boeing 747 at cruising altitude would need over 70,000 years to fly the same distance. This is not a hole in space. This is a region the size of a small star cluster, fenced off from the rest of reality. And here is the thing most accounts skip. The thing that makes Phoenix A genuinely more unsettling than any smaller black hole. At this scale, the surface gravity at the event horizon is actually mild. I know, that sounds wrong, but it is mathematically true. The tidal forces, the violent stretching that would tear your body apart near a stellar mass black hole, are gentle near the event horizon of Phoenix A. Spread across a boundary this enormous, the gradient of gravity is gradual. You could drift across the event horizon of Phoenix A without feeling a single jolt, without your instruments registering anything unusual, without any sensation whatsoever. You would not know you had crossed. You would not even know you were doomed. The death would come later, somewhere deep inside, hours or days after you slipped past a boundary you never saw, never felt, never registered. That is what makes ultramassive black holes feel less like objects and more like territories, less like predators, more like empires. Here is the question that genuinely haunts every astronomer who studies this object. How did something this big get this big? The standard model is straightforward enough. A black hole begins as a stellar remnant, pulls in surrounding gas, grows slowly, galaxies collide, central black holes merge, billions of years pass. The math works, barely, for the supermassive black holes we're used to. For Phoenix A, the math breaks. The universe is 13.8 billion years old. To grow a black hole of 100 billion solar masses, you would need it to feed at near maximum theoretical efficiency, continuously, for almost the entire history of the cosmos. No breaks, no pauses, no dormancy. Real black holes don't do that. As matter spirals inward, it heats up, radiates, and that radiation pushes back against incoming material. This is the Eddington limit, a natural speed cap on how fast a black hole can feed. Real black holes burp, choke, and throttle their own growth. They take breaks. Even if Phoenix A began as a million solar mass seed at the very first moment of cosmic time, and fed at the absolute maximum theoretical rate without ever stopping, it should weigh only about 10 billion solar masses today. Phoenix A is 10 times heavier than physics says it can be. It broke the cosmic speed limit. So astronomers are left with 3 uncomfortable explanations. Option 1. Phoenix A formed from direct collapse. Enormous clouds of primordial gas in the early universe that bypassed the stellar phase entirely and collapsed straight into black holes already millions of solar masses from birth. A monstrous head start. But even that makes the numbers extraordinarily tight. Option 2. Multiple supermassive black holes from colliding galaxy clusters funneled into the same gravitational well during the most violent period of cosmic history and merged catastrophically into something extraordinary. A single event rather than a slow accumulation. Option 3, the one that keeps physicists up at night, is that Phoenix A found a way to exceed the Eddington limit itself. Recent observations of certain black holes suggest some contemporarily feed beyond the theoretical cap. If Phoenix A did this not briefly but for billions of years, its forbidden mass starts to make sense. In other words, it didn't just break the rules, it may have been rewriting them the entire time. Either way, by every framework we currently have, Phoenix A has business being here. And yet, there it is. Now consider what Phoenix A is actually doing right now. It is feeding. Not slowly, not gently, furiously. The Phoenix cluster, like most massive galaxy clusters, is filled with hot plasma heated to tens of millions of degrees, hot enough to glow brilliantly in X-ray light. This plasma fills the space between galaxies in a thin but enormous reservoir stretching across millions of light years. In most clusters, this gas cools gradually over time. As it cools, it falls inward under gravity, condenses, and eventually forms new stars. That is the prediction. That is what physics says should happen. In most clusters, it doesn't. The central black hole acts as a thermostat. Cooling gas triggers feeding events, which launch jets of energy outward, which reheat the surrounding gas, which halt further cooling. The feedback loop holds. Equilibrium is maintained. In Phoenix, the thermostat is broken. The cooling gas is winning. The central galaxy of the Phoenix Cluster is forming new stars at a rate of approximately 700 to 1,000 solar masses per year. Our entire Milky Way forms about 1 solar mass of stars per year. The Phoenix Cluster's central galaxy is building new stars 1,000 times faster than ours. Stars igniting across that galaxy on timescales that are, by cosmic standards, almost instantaneous. And in the middle of all that newborn fury sits Phoenix A gases cascading onto it at a furious pace. Jets are punching outward at nearly the speed of light, carving cavities the size of small galaxies in the surrounding plasma. But the jets are not strong enough to stop the inflow. Phoenix A, for all its inconceivable mass, cannot keep up. The most massive black hole ever observed appears to have lost control of its own environment. It is like finding a wildfire that somehow stopped burning, allowing a forest to grow explosively in its path. Except in this case the fire is a 100 billion solar mass black hole, and the forest is being born at 1,000 stars per year. Here's what makes Phoenix A genuinely extraordinary beyond its raw size. This kind of runaway cooling, this kind of awakening. This is exactly what astronomers believe happened in the early universe, when supermassive black holes were assembling for the very first time. When galaxy clusters were young, chaotic, full of cold gas, and everything was still violently being built. Phoenix A may be giving us a live view of a process we thought was over. A replay of the ancient universe, playing out in real time, 5.7 billion light-years away, in light that started its journey before Earth existed, before our sun had ignited, before the solar system assembled from a collapsing cloud of gas and dust. That light left Phoenix A before our planet existed. It travelled for 5.7 billion years through the expanding universe, and by the time it reached our telescopes, our planet had formed, cooled, grown an ocean, evolved life, developed intelligence, built civilization, invented science, and produced creatures capable of pointing instruments at exactly the right patch of sky to receive it. And those instruments saw, at the moment that light left, that Phoenix A was awake, feeding, building stars, breaking its own environment, doing something the rules said it shouldn't be able to do. What Phoenix A is doing in the actual present, in true real time, no human instrument will ever directly observe. The present state of Phoenix A is permanently behind the finite speed of light and the expanding gulf of space, hidden from us by the most fundamental constraint in physics. What we are watching is a message from the past, and the message says, we still do not understand how the universe builds its largest structures. If you could somehow stand outside the central galaxy of the Phoenix Cluster, far enough to see the whole picture, close enough to feel it, here is what you would witness. The galaxy itself would glow with the heat of hundreds of millions of newborn stars packed into a region not much larger than the Milky Way. Every direction you looked, new suns, not the steady ancient starfield we see from Earth, a sky being continuously rewritten, stars flickering on across the dark in what feels, on cosmic timescales, like a rapid fire. The space around that galaxy would shimmer with X-rays from cooling plasma, gas falling inward in vast streams, heating as it compresses, glowing at temperatures that would vaporize any matter we know before it even got close. From the very center, jets, twin columns of high-energy particles punching outward at nearly the speed of light in both directions, slamming into surrounding gas, carving cavities the size of entire small galaxies in the hot plasma, creating shock waves visible across millions of light-years. And above all of it, invisible but unmistakable in its gravitational effects, would be Phoenix A itself, not gleaming, not truly dark. Just a region where the universe, in any meaningful sense, ends. If you drifted closer, drawn by the kind of curiosity that overrides self-preservation, you would feel nothing change for a very long time. The pull would build slowly, imperceptibly. The light from the rest of the universe would gather into a small bright circle behind you. The stars would shift, redden, crowd together into a tightening ring as your angle of view contracted. There would be no warning, no shudder, no alarm, no visible marker. You would simply pass a line that no longer let you signal anyone you had crossed it. And the universe would forget you instantly, hours or days later, somewhere deep inside, far below where the equations still told the end would come, not with drama, Not with noise, just physics. At a scale where none of the rules you were born under apply anymore. That is Phoenix A, not an object, not a thing, a domain, a territory, a region of the universe that has seceded from every law everyone else lives by. Here is the part that changes the story from remarkable to genuinely unsettling. If Phoenix A exists, it is not unique. We found it because of one unusual property, the runaway cooling flow that made the Phoenix cluster the brightest X-ray source of its kind ever recorded. It announced itself. It waved a flag. But the black hole at its center may be only one of many ultramassive black holes scattered throughout the universe. Most of them quiet, most of them dark, most of them invisible to our current instruments, precisely because they are no longer feeding. A dormant ultramassive black hole in a cluster where the thermostat is working normally produces no dramatic signal, no runaway star formation, no jets bright enough to be seen across billions of light years. It simply sits there, in the dark, waiting. Some theorists have begun using the term stupendously large black holes, objects potentially pushing well beyond 100 billion solar masses, approaching the theoretical upper limits of what general relativity, our best description of gravity, actually permits to exist. We don't know how many there are. We don't know exactly how they formed. We don't know what role they will play in the long-term fate of the galaxies around them. And current computer simulations cannot produce Phoenix A. The most sophisticated models of cosmic structure formation, run on the most powerful supercomputers available, do not generate black holes of this mass within the time constraints the universe provides. Something is missing. Something about the early universe. Something about how matter collapsed and black holes assembled in the first billion years that our current physics has not yet found. Phoenix A is not just an extreme data point. It is a falsification, a piece of reality pointing directly at a gap in our understanding and refusing to let us look away. For most of human history, the largest things we could imagine were the things we could see: mountains, oceans, continents. Then we discovered the Earth was a sphere, that the Sun was 100 times larger, that the galaxy held hundreds of billions of stars, that there were hundreds of billions of galaxies. Each step outward made us smaller. Each step taught us that what we called big was actually a footnote in something larger. Phoenix A is the next footnote. A black hole so massive the standard concept doesn't cover it. A region of space so large light needs weeks to cross it. A presence so heavy it holds together a structure larger than anything in our local cosmic neighborhood. And it is still awake, still feeding, still growing in ways the mathematics says shouldn't be possible. But the part that genuinely stays with me, the part I keep returning to, is not the size. It's the continuity, the patience. Phoenix A has been doing what it does since before the Earth existed. While our solar system assembled from a cloud of debris, Phoenix A was feeding. While the first oceans formed, while single-celled life appeared, while evolution worked across billions of years toward complexity, Phoenix A was feeding. While fish climbed onto land, while dinosaurs rose and fell, while mammals spread, while primates descended from trees, while humans built fire and cities and telescopes, Phoenix A was feeding. It waited through the rise and fall of everything. It will still be there when the sun expands and swallows the Earth. It will still be there when the Milky Way and Andromeda merge. It will still be there, patient and dark and vast, when the last stars in the universe flicker out and the cosmos grows cold. And in the entire span of human civilization, every war, every empire, every discovery, every moment of every human life ever lived, Phoenix A moved through an eye blink of its own existence without registering it. That is the thing about Phoenix A. Not the size, not the broken mathematics, the fact that something so enormous can be so patient, can wait through the rise and fall of entire civilizations, can outlast suns and planets and species, and still be hungry at the end of it. You started this video thinking you knew what a black hole was. Now you know what Phoenix A actually is. Let every thread close. Phoenix A weighs approximately 100 billion solar masses, roughly 50% more massive than 2On 6 and 18, the previous record holder, and 25,000 times more massive than the black hole at the center of our own galaxy. By the standard physics of black hole growth, the Eddington limit, the age of the universe, and the mathematics of accretion. Phoenix A cannot exist. The universe is not old enough to have built it. It broke the cosmic speed limit by a factor of 10. Its event horizon spans approximately 370 billion miles, 100 times the distance from the Sun to Pluto, making it not an object but a territory, a domain, a region of space-time so large that crossing its boundary feels like nothing at all. That gentleness is the horror. You would drift past the point of no return without a single sensation, without any warning, without knowing you were already gone. The Phoenix cluster is forming stars at 1 zillion solar masses per year, 1,000 times faster than the Milky Way, because Phoenix A's thermostat broke and the cooling flow it should be suppressing has become a runaway torrent it cannot stop. Phoenix A may be showing us the early universe in real time. A live replay of the violent conditions under which the first ultramassive black holes assembled in light that began its journey before our planet existed. Phoenix A is almost certainly not unique. Most ultramassive black holes are dark, dormant and invisible, scattered through the universe in unknown numbers, sitting in silence, waiting for the conditions that woke Phoenix A to reach them. Current simulations cannot produce it. Something is missing from our understanding of the early universe, and Phoenix A is pointing directly at the gap somewhere right now, 5.7 billion light-years from where you are sitting. A hole in the universe is open. It opened long before the Earth formed. It will still be open long after the Earth is gone. And in the entire time it took for that light to reach us, every atom of your body, every breath you have ever taken, every moment of every human life ever lived, came and went while Phoenix A simply continued doing what it has always done. Not the size, not the broken math, not the 1,000 stars born every year. The patience, something so enormous, so quiet, so indifferent, waiting through the rise and fall of everything, and still hungry at the end of it. Phoenix A is not the largest thing we have ever found because we were unlucky. We found it because it announced itself, because its runaway feeding made it impossible to miss. The ones that didn't announce themselves are still out there, dark, patient, waiting. Sometimes the most unsettling thing about the universe isn't what's loud, it's what's been waiting. Phoenix A has been sitting in the dark for billions of years. It woke up. We have no idea what wakes the others. Thanks for watching. See you in the next one.